The AFSA Animal-Free Safety Assessment Collaboration is a collection of industry and nonprofit partners who have the aim of accelerating the global adoption of a modern species-relevant approach to safety assessment in three primary areas: cosmetics, chemicals, and biologicals. The Animal-Free Safety Assessment Education and Training Program that this series of webinars is introducing is part of the cosmetics work stream of this larger project. So the Education and Training Program itself, the scope of the program is safety assessment of cosmetics and cosmetic ingredients without new animal data. And the program covers all aspects of the risk assessment process, from problem formulation through the final risk assessment. And it includes things like consumer exposure, both external exposure and internal exposure. It covers acute and local effects, such as skin and eye irritation, skin sensitization, all the way up to systemic repeat dose effects. And the overall goal is to integrate all of this information to make a risk decision. So it covers all of this. And the focus, what makes this course unique is really that the focus is on understanding the information that's generated from these tools and how to use this information to make decisions. What this course is not is a tutorial on how to perform the methods. This course is intended to complement other existing courses and webinars that cover how to perform the individual methods. The ultimate purpose of this course is to address the needs of the regulatory and regulated communities, as well as other stakeholders involved in the risk assessment process. And ultimately, we want to support regional capacity building to achieve the long-term acceptance and implementation of non-animal approaches to safety assessment. So to give a little bit of context around what this course is trying to do, I just wanted to briefly give a very high-level overview of what we're calling animal-free safety assessment and how that compares with the historical approach to safety assessment. Basically, the overall process is very similar between the two. Both rely on measurements or estimates of exposure, as well as an estimate of a chemical's intrinsic hazard to determine the risk associated with a particular use or exposure. The main differences are in how and when exposure comes into the process, and the types of information that are used to estimate a chemical's hazard or bioactivity. In traditional risk assessment, a set of standard animal tests is usually carried out, and the lowest dose or the lowest dose causing an effect or the highest dose causing no effect in any of these tests is taken as the point of departure to base the risk assessment on. Exposure is generally considered only after or at the same time as the hazard assessment, and both feed into the final risk assessment. In the animal-free risk assessment process, especially for consumer products, exposure is considered from the beginning, and the assessment is performed in stages or tiers. Exposure considerations are used either to make an early safety determination or to design testing strategies that generate the information that might be needed to make a safety determination. In silico tools are used in the initial characterization and in read across. Any needed information on biological activity or internal exposure is generated using non-animal assessment methods. Finally, the results of the biological activity is compared with measured or predicted internal or external concentrations, exposure concentrations, to generate a margin of exposure, which is used to conclude a risk for a given scenario. In the AFSA Education and Training Program, we have taken this process that's loosely diagrammed in the gray boxes above and divided that into 8 modules for content development, and those are diagrammed in the dark purple boxes. We've included a 9th module on the global regulatory environment of cosmetics and cosmetic ingredients, And that is the subject of next week's webinar. To provide a little more detail of what's actually in the course, this is what a complete animal-free safety assessment workflow looks like. This workflow was originally designed in a European framework program project called SIRAT, which is safety evaluation ultimately replacing animal testing. And this process is loosely divided into 3 tiers. Tier 0, it starts with the problem formulation, which includes analysis of the chemical itself, understanding the molecular structure, also the decision context, and evaluation of all existing information. And in this tier, you can begin your initial mode or mechanism of action hypothesis. This tier usually also includes an initial exposure estimation. And at this stage, it may be possible to reach a safety conclusion, either based on toxicological threshold of concern or by read across. If the assessment requires the generation of new information, the tier 1 involves initial in vitro hazard or bioactivity identification and characterization, and analysis of internal exposure, which is what we'll be hearing about today, our systemic bioavailability. It may be possible to reach a conclusion here by the internal toxicological threshold of concern. However, if, or by comparing the initial in vitro point of departure that's estimated by using the concentration response analysis of these in vitro tests compared with the internal concentration to come up with your original margin of exposure. If it's necessary to generate more information to be confident in this risk conclusion, you move on to tier 2, where you get more in-depth or more different types of bioactivity estimation, and you can further refine your internal exposure estimation to come up with a point of departure. Point of departure for your margin of exposure that has a higher certainty. And you do this iteratively until you have sufficient data and certainty to come to a risk conclusion of either high risk or low risk based on the margin of exposure. The course covers this process in the following way. The problem formulation module covers the original decision context and everything, the evaluation of existing information and initial mode of action hypothesis. The consumer exposure module covers use scenarios, consumer habits and practices, and also the data that goes into the different types of modeling and the different modeling approaches for consumer exposure. There is a module that just covers the in silico tools, different types of SAR and QSAR. That was the webinar a couple of weeks ago, and also covers read across. There's another module that just deals with exposure-based waving that covers the toxicological threshold of concern approach and how that's applied for 3 different routes of exposure, oral, dermal, and inhalation. There's a separate module on the history of safe use for complex extracts such as botanicals. This is the module we're going to have an overview of today, and that is the internal exposure dosimetry and IVIVE in vitro to in vivo extrapolation. Then there's a module on in vitro data synthesis, in which this means is how the data from in vitro methods are combined to address different types of biological activity, either endpoint specific like skin and eye irritation, skin sensitization, or more general systemic effects that can be used to derive a point of departure. And then finally, there's a module on integrating all of this information into a final risk assessment. You get the picture that this course is quite comprehensive. It's also fairly in-depth. The modules are at different stages of development. This webinar series that covers 4 of the most advanced modules that will be they're nearly ready for dissemination to the public. The rest will be coming later this year and will be the subject of future webinars. So these are the partners that are supporting the development of these materials. And these are the actual people who are authoring the content of these materials. We're also working with an education expert and a graphic designer to create the materials. So, okay, now we'll move on to the main course of this webinar, which is an overview of the dosimetry internal exposure module of this course, which will be presented by Allison Schafer and Rebecca Clewell. Allison Schafer is a human safety toxicologist in beauty care at Procter & Gamble with experience in cosmetic ingredient risk assessment and inhalation toxicology, and holds a PhD in pharmacology. Rebecca Clewell is a complete and total expert in dosimetry, internal exposure, and IV/IVE. I've known Rebecca for many years. When I first met her, she was at the Hamner Institute, for those of you who know that powerhouse of toxicology. And then she's had several iterations since then, including being an independent consultant for a few years. And she recently moved to the US Army, but Rebecca, sorry,
Air Force.
Air Force, yes. Oh gosh, the Air Force. I'm so sorry.
No problem.
And anyway, Rebecca literally has PBK modeling in her blood. So leading expert. Okay, so now I will turn it over to Allison to begin our presentation.
Thank you, Kate. Hello, everyone. I think we can go to just go with the next slide. All right, so here we have our overall learning objectives for today. By the end of our presentation, we hope that you'll have a good understanding of biokinetics and PBPK modeling, specifically in order to describe the role of biokinetics in risk assessment, an understanding of the 4 components of dosimetry, listing the applications of PBK modeling and the types of compartments that are involved in PBK modeling, outlining the differences between IV/IVE and PBK, and then identifying the applications of IV/IVE. Next slide. So why is dosimetry important? Predicting the internal exposure or dose that results from an exterior exposure to a substance is important because it's the internal amount of the substance that's available for interacting with the cells, tissues, and organs in the body that can potentially cause an adverse effect. The science of predicting internal exposure or absorbed dose is known as dosimetry. There are many individual attributes that can impact the internal dose of a substance. So to get a more accurate picture of what may be going on in a particular situation, estimation of internal dose using dosimetry can be important. Estimating the internal dose involves the combination of measuring and estimating the kinetic processes that go on inside the body. This includes absorption and distribution throughout the body, metabolism, and excretion of the substance. Next slide. So this shows the source to outcome continuum. In this toxicological source to outcome continuum describes the chain of events that occur from exposure to chemical induced toxicity. So external exposure is the amount of chemical that an individual may encounter. This doesn't necessarily dictate the toxic response, which is instead determined by the amount of the active form of the chemical that reaches the target tissue or that internal dose, and its interactions with cellular components that can lead to a toxicological event. The study of pharmacokinetics or toxicokinetics is the quantitative evaluation of chemical kinetic processes that determine internal dose following this chemical exposure. And the goal of pharmaco or toxicokinetics is to develop the internal dose metrics to help predict tissue toxic response. So overall in this talk and in the larger module, we will illustrate the biokinetic processes that govern chemical distribution in the body and describe the mathematical tools that are used to incorporate a quantitative description of chemical tissue dose into risk assessments. Next slide. So when an individual is exposed to a certain compound, there are a couple things we must consider. First, the time or duration of the exposure, and then the level or amount of chemical to which that person is exposed. There are 3 key pathways for exposure to exogenous chemicals. This includes oral ingestion or absorption through the GI tract, transdermal absorption or absorption through the skin, and inhalation through the lung. These can occur, chemicals present in food, water, or other beverages are likely to enter the body through the GI tract or oral exposure, as are chemicals present in medications or vitamins. For volatile chemicals, gases, or compounds that are released into the atmosphere as small particles or aerosols, exposure is likely to occur through inhalation. And then chemicals that come into contact with the skin can be absorbed into systemic circulation. So generally, the skin acts as an effective barrier between the environment and systemic circulation. Nonetheless, exposures can occur through water, such as through bathing or swimming, cosmetic products, and other scenarios where chemicals come in direct contact with the skin. So chemical toxicity can occur through direct activity at the site of exposure, such as the skin, GI, or airway, or through systemic effects following absorption and transport in the blood, both of which can be predicted using pharmacokinetics. Next slide. Different product types are associated with these different routes of exposure, including dermal inhalation or ingestion. Dermal exposure is most relevant to our consumer goods, including skin creams, deodorants, soaps, dishwashing liquid. Some aerosol deodorants or aerosol shampoos can lead to inhalation exposure. Other products like mouthwash and lipsticks lead to oral exposure or even incidental exposure from products such as dishwashing liquids. All these exposures contribute to systemic and local dermal effects and hence need to be appropriately considered in our assessments. Next slide. So biokinetics is the study of the metabolism and transport of drugs in pharmacokinetics or chemicals, in the case of toxicokinetics, through the body. Regardless of the route of entry, each exposure will lead to an internal concentration at the organ, tissue, cells, and macromolecular levels, which can then have a toxic effect. The internal dose that has the potential to cause a toxic response is important to measure and assess. Tissue dosimetry provides a better correlation in response to that external exposure. And there's a couple of differences between kinetics and dynamics. So biokinetics is considered what the body does to the chemical, while biodynamics is what the chemical does to your body. And in PBK modeling, we are more interested in that first part of biokinetics, where the role of biodynamics begins once we have the specific exposure to the target tissue. So these two processes work well together. Next slide. And so now we'll go into some more detail on the basics of biokinetics. As I said, dosimetry is that looking at that internal dose within our tissues throughout the system. ADME is the short form of these 4 processes that drive biokinetics. This includes absorption, distribution, metabolism, and excretion. These processes overall determine where a chemical will go in the body and what form it will be in when it gets there. And this chemical disposition or biokinetics is the product of these composite action of the chemicals ADME. Next slide. So absorption is the first component of dosimetry. And absorption is the uptake of biochemicals into the body. It can happen via the oral, dermal, or inhalation routes. It can be passive or active biochemical processes. Bioavailability is an important term in biokinetics. It is used to describe how well a chemical is absorbed into the system. By definition, it's the fraction of the administered dose that enters systemic circulation. So an intravenously administered dose is, by definition, 100% bioavailable. However, limitations in absorption by the site of exposure can reduce bioavailability. And overall, in the larger module, we'll discuss this further to understand how this can affect biokinetics. Next slide. So today I will go into more detail on absorption via the dermal exposure, as this is most relevant to our cosmetic products. However, other routes of exposure will be discussed in the larger module. The skin is our largest organ and acts as a highly effective barrier because it is largely impenetrable to environmental chemicals and water. The skin is made mainly of two layers, the epidermis and dermis. The epidermis is the outermost layer, which consists of keratinocytes. The innermost keratinocytes are metabolically active and proliferate, generating new cells. The outermost keratinocytes make up our stratum corneum, which have lost their nuclei, are metabolically inactive, and no longer proliferate. The proliferating keratinocytes displace the stratum corneum every 3 to 4 weeks, but the stratum corneum is our most important barrier to water loss and environmental chemical uptake. Typically, we assume 100% skin penetration at the initial risk assessment. If this outcome is acceptable, then no further quantification is required. However, if 100% bioavailability leads to unacceptable predictions of risk, further evaluation of skin penetration may be needed. In some cases, experimental estimation of skin penetration of an ingredient from a formulation is required. This is generally conducted using in vitro experiments or by PBK modeling, which we will discuss later on. Next slide. So there's a number of in vitro methods for estimating skin penetration and bioavailability of cosmetic and consumer product ingredients. For example, solubility evaporation of a chemical may be evaluated using in-chemico tests. Absorption can be measured in skin patches. Human skin, often derived from surgeries, is placed on the membrane in the center and clamped on either side. We have receptor fluid flowing through the skin and coming out the other side. The ingredient of interest is placed on the skin, and then this can be in formulation or as a single ingredient. And the receptor fluid is sampled at different time points and analyzed for the presence of test substance. And then metabolically active skin can be used to simultaneously measure diffusion and skin metabolism. And these methods have found particular use as a screen for comparing delivery of chemicals into and through skin from different formulations, and can provide useful models for the assessment of skin absorption in humans. Next slide. So next we have distribution, which is the transport of a chemical to various tissues of the body from the blood. This can be passive diffusion or active transport between the blood and tissues. Passive diffusion occurs and it's governed by electrochemical gradient, whereas active transport uses energy to move chemicals against the electrochemical gradient. Many factors can influence distribution, such as blood flow, lipophilicity, molecular size, and how the drug interacts with the components of the blood. Blood flow distributes chemical through the body and is affected by tissue perfusion. Distribution is also affected by protein binding in the blood and tissues, and only free compound is available for transport. And I'll go into a little bit more detail in the next slide. So for distribution, there are a couple of things that can help determine the distribution of chemicals. There are chemical-specific parameters that help determine distribution. For example, log P, which is a measure of lipophilicity of a compound. This is also called the Octanol water partition coefficient. In general, passive diffusion is favored by chemicals with a positive log P, since the cell membrane exterior is lipophilic. And these lipophilic chemicals will partition into the fatty tissues. Distribution can also be affected by physiological determinants such as body weight, tissue volume, and blood flow to tissues. Next slide. So chemicals can form reversible bonds with various proteins in the body. Of all the proteins with which chemicals can bind, plasma albumin is the most important. Like other proteins, albumin is a large molecule. It's too large to leave the bloodstream. And what this figure is depicting is the binding of chemicals to albumin. The chemical is generally much smaller, and as indicated by the two-way arrows, this binding is reversible. Generally, it is assumed that only free chemical is available for tissue uptake or metabolism. So for chemicals with high degree of plasma protein binding, tissue uptake and metabolism and clearance will be reduced. We use the term fraction unbound as a way of communicating the extent to which a chemical is bound to serum proteins, which is also an indication of the likelihood that the chemical will be widely distributed. Next slide. So the third component of dosimetry is metabolism, and this is enzyme-mediated transformation of the chemical. The liver is generally the major site of metabolism. However, other tissues can have metabolic capabilities, including the kidney, skin, GI, and lung. The kidney and liver metabolism will likely alter clearance. Metabolism in the GI, skin, and lung limit absorption. Metabolism is a key determinant of chemical clearance from the body, but can also introduce potentially bioactive metabolites to the system. In general, metabolism increases the ability of the body to excrete a chemical. However, in some cases, metabolism can also make a compound more reactive. And when we discuss PBK models later in this module, it's important to remember to account not only for the parent or administered compound, but also for any bioactive metabolites. Next slide. So how do we measure metabolism? Metabolism parameters can be estimated using a number of in silico or in vitro methods, ranging from high throughput computational methods based on physicochemical factors to simple cell-free test systems to 2D monoculture cells and 3D reconstructed tissue cultures. For certain chemicals with predictable metabolism, in silico or simple cell-free systems may suffice, while chemicals with more complex metabolism profiles may require more complex test systems. As with all aspects of modeling, the system should be fit for purpose and only as complex as necessary, since more complex systems introduce added cost, time, and necessary expertise. So note, it's important to note that rates of metabolism measured in vitro don't necessarily have the same limitations as in vivo. Therefore, in vitro measures must be scaled to account for differences in vitro and in vivo conditions. Scaling will be discussed more in the larger module. So next slide. And finally, we have elimination, which is the final component of ADME dosimetry. The kidneys filter the blood and excrete chemicals into the urine for elimination, and the liver excretes chemicals into the bile, which is transported to the GI and either reabsorbed into the system or eliminated in the feces. Elimination can also occur via the lung. Volatile compounds, which are poorly dissolved in the blood, will be released into the exhaled air by the lung capillaries. Next slide. So as far as urinary excretion, there's no current widely available in vitro models for this method or for renal excretion. Glomerular filtration is predicted by chemical size, and passive diffusion is predicted by chemical structure. However, active transport into or out of the lumen is much harder to predict unless the binding of a specific transporter is known. So we try to predict this, however, there's no available models. And next slide. So this is just an overview of ADME and biokinetics. To recap, biokinetics is the study of metabolism and transport of drugs or chemicals through the body. And you can keep, yeah. Despite the protective barriers such as skin, there are multiple routes of entry for chemicals, including GI and the lungs. And all of these go into predicting the internal exposure, which is then ultimately used in our risk assessment. So now I will hand it over to Rebecca, who will give more details on biokinetic modeling and IVE.
Thank you, Allison. So I'm going to begin with talking to you a little bit about the history of PK modeling. Go ahead, next slide, please. So classical compartmental models were developed to predict certain parameters that are important for understanding chemical kinetics and relative kinetics across different chemicals. So the idea was to estimate a volume in which the chemical is distributed within the body. And the idea here is that some dose enters the body, is distributed and eliminated from the body in a certain amount of time. And compartmental models don't try to estimate exactly the organs or tissue amounts or actually even blood amounts. What they try to do is estimate the apparent volume of distribution of a chemical within the body. And what this allows us to do is identify how well the chemical is distributed and how quickly it leaves the body. These kinds of models are important for deriving certain parameters that we use for pharmacokinetic comparisons and are often used in pharmacology. They allow us to estimate, for example, half-life and Cmax and area under the curve. So you've probably heard of these parameters, and they're often used to briefly describe how the kinetics of a drug. However, well, and I'll quickly mention that if you have a large volume of distribution, then the chemical is distributed widely. It's likely distributed within the body water, which is approximately 75% of the body. On the other hand, if there's a small volume of distribution, the chemical is poorly distributed, and it's likely bound to proteins in blood if it's well absorbed. These models are highly useful for rapid communication of different chemical kinetics. However, there are a lot of issues that are overly simplified here, or maybe not even taken into account, which can include absorption, transport into tissues, and the processes involved in clearance. Of course, these models can be made more complex to account for certain understanding of the chemical kinetics. However, because they don't incorporate physiology of the body, there's a lot of assumption that must be taken into account, and they're useful for understanding the behavior of a measured pharmacokinetic profile, but they are not useful for extrapolating outside the conditions of the experimental procedure. So if you could, next slide. So the idea behind classical compartmental models, and I'm starting with this just to help you understand the context from which PBPK modeling arrived. The rate equations are described using a fully empirical process where you have a data set, you fit the parameters in the equations to the data, and by iterative processing, so you change the parameters till the curve fits the data well. It's an entirely empirical process, and it's not predictive outside of the data set for which it was built. Next slide. Oops, we have some animations there. So some of the benefits, as I mentioned, these are easy to create. There are many existing softwares. You've probably heard of a number of different software options that allow you to quickly estimate these models and the parameters associated with them. It allows calculation of very informative parameters for kinetic analysis, including area under the curve, which is an average concentration in the blood over time, the Cmax, which is the maximum concentration, and the half-life for a chemical. And these are particularly helpful when you're trying to understand and predict the behavior of a drug under different dosing conditions. The limitations of these models, as I've mentioned a couple of times, are that you can't extrapolate outside the experimental conditions. So for example, if you have information in a rat and you want to predict what's going to happen in the human, it's very limited in how you can do that. In addition, extrapolating outside the different types of dosing, dose routes from intravenous to oral or from oral to inhalation, those are outside the application of these types of models. And we can only describe the data. We can't predict the behavior. And so as we're moving forward and we're trying to better understand how chemicals, or to predict chemical behavior without the collection of animal data, there's obvious limitations to these types of models. And so back in the 80s, a new methodology was proposed. Next slide. So PBPK models, and I apologize because I'm still trying to get out of the habit of saying PBPK, and I'll get into that in a second, but we now call them PBK models. They're physiologically based biokinetic models, and they describe the physiology of the body, including the various tissues and the flow from the chemical in the blood, in and out of these tissues, and the excretion and metabolism that occur within the body, which was just described by Allison. So we take these descriptions, we translate them into mathematical equations, and we are able to predict where the chemical will go within the body and where and the time course of the body, time course of the chemical within the body. Next slide. So just a little bit of background on the terminology here. There's a little added thing in the top left, so ignore that. But so PBPK modeling is a physiologically based pharmacokinetic modeling, and this was the original term that was used when it began to be applied to environmental chemicals back in the 1980s. And this was pioneered by Dr. Mel Anderson and Dr. Ramsey from Dow and Dr. Harvey Clewell, who does happen to be my father. And they worked on this and took some very early models that were actually developed back in the 1920s to describe anesthetic behavior in patients, and use well, basically use the basis of those models to start describing the kinetic behavior of environmental chemicals in rats, and explore the utility of those models to predict human behavior. And eventually over time, go ahead and click the slide, please. Yeah, so these models began in the 1920s for anesthetics. Next click. And in the 1980s, they started applying these towards environmental chemicals. Next, yes. And there's, just keep on clicking because there's like a number of examples here. And so the terminology kind of hung on physiologically based pharmacokinetic models because this is where it came from. Though over time, there was some questioning about that terminology because really we were looking at these models in terms of their toxicology. And so it was proposed that we change the terminology to physiologically based toxicokinetic modeling. Next slide. And then as we've moved on and started to agree that these models really are just describing the interaction of biology and kinetics, we've simplified the term to physiologically based biokinetic modeling. Next slide. And these models now have been applied to any number of drugs. I think there was a recent review by Alicia Paini and others that counted approximately 126 published PBPK models in the field. Next slide. So we've shortened it to PBK, and I am trying to adjust to that. But after 20 years of saying PBPK, it's a difficult transition for me. So just understand that all of these terms really refer to the same process. The only difference is whether you're applying them to chemicals that are likely to be toxic or chemicals that are likely to be pharmacokinetic or pharmacological. So really, regardless of the term that you use, the technology is the same. So why use PBK modeling? As I mentioned, but oh, sorry, we're going to get into that in a second. So a quick overview of what the module course content will be. So today we're providing just a high level overview, an example, a preview, if you will, of what the course is going to look like. But the course itself is quite intensive and actually designed to describe PBK modeling and the process that is involved in it and the validation of it, so that after you finish this model, you will have an understanding, an in-depth understanding of PBK modeling. And in fact, we include enough information in there that if you were interested in trying to learn to develop PBK models, you should have the information at your fingertips that will allow you to do that. So the course itself will cover why should we use PBK models, which I've already described to you a bit. It will cover building a PBK model, including defining the structure and parameterization of that model. It will describe validation of models, including how do we compare these models to data and how do we describe success of those model fits, and tools that we use to evaluate the utility of a model, including sensitivity and uncertainty analysis. The course will also cover applications of PBK, including extrapolation across species, routes of exposure, life stage, and accrued chronic exposures, and will as well as target tissue dosimetry for supporting risk assessment, interpretation of biomonitoring studies, and the kind of more popular and more recent application of PBK models, which is in vitro to in vivo extrapolation, which is the application of the PBK technology to in vitro bioactivity assays. So next slide. So why PBK models? As I've mentioned a few times, the main advantage of using PBK models is extrapolation, being able to predict what a chemical behavior will look like beyond the experimental conditions that you have it at the ready. So this is opposed to interpolation, which is describing kinetics within the experimental conditions, which is allowed in classical PK. So different extrapolation activities that you're able to do with these models is root to root. So if you have information, as I mentioned, from oral absorption, and you want to predict what inhalation will look like, then that is possible with these models. Species extrapolation, so the classical use of PBK models is developing data in laboratory animals, including mice and rats, and then predicting what the pharmacokinetic behavior will be in humans. In addition, life stage or other intra-species extrapolation. So if you have information in an adult, or you have an understanding of what kinetics would be like in an adult, but you're interested in finding out what the dose to, say, a fetus or a neonate might be through lactation exposure, then those are extrapolations that are possible. You can also have other explorations, including differences in metabolism that might be a result of ethnicity and different metabolic enzyme capacity, or say gender differences. If you're interested in single to repeated exposures, that's also a very useful application of these models, and you can often extrapolate across chemical families as well. So pharmacokinetic modeling is a valuable tool for evaluating tissue dose. That's another reason that we use these models, with the understanding that the relationship of external dose to toxicological response is actually mediated by the amount of the active chemical, or the concentration of the active chemical that's in the target tissue. And so predicting this using a PBK model is a very valuable use of these models. And we can also incorporate toxicological responses and those effects of the toxicological responses on the chemical kinetics into these models as well. So if you're familiar with biokinetics, then you know that there can be induction of metabolism that occurs because of chemical exposure, and these kinds of considerations can be incorporated into the models as well. And we often use physiological modeling to uncover biological determinants of chemical disposition. So using these models really as research tools to better understand or to identify where there might be specific processes that are governing chemical uptake or clearance. So if you think, for example, of active transporters that lead chemicals to be concentrated in particular tissues is one example of that. Next slide. So the PBK modeling process is iterative, and it's basically the scientific method in a nutshell. So you begin with your problem identification. You search the literature to find what information you have that can support the model development. And this usually is kind of split into three main activities: understanding the mechanisms of toxicity, and in particular, identifying the tissues that are important for describing within your model; identifying biochemical constants, so understanding how the chemical is taken up and cleared and distributed within the body; and also, of course, understanding the physiological constants. You develop your model, you perform some simulations, you compare to the data that you have, and you refine your model as necessary. You can also use this process to better design and conduct critical experiments that can help elucidate the important mechanisms within your model. And after you've developed a model that sufficiently describes the data that you have, you can validate your model and perform the extrapolation that you're interested in. So the important thing about this is that it's a very iterative process. You never would expect that the first structure you build for a PBK model is going to be the final or ultimate product. And in fact, usually if your first try works perfectly, I'm a little concerned because that's just how a scientific experiment goes. And these models are an experiment. They through iterative process, you learn more about the system and about how the chemical is distributed within the system. Next slide. So probably the most important principle in PBK modeling to keep in mind is the principle of Occam's razor, which is entities should not be multiplied without necessity. Or another way to say this is the simplest explanation is usually the right one. So it's very tempting and very possible to develop very complex models that have any number of parameters. And the more parameters you add to a model, inevitably, the better you will be able to describe the data. That's just the way it goes. Unfortunately, as you add more and more parameters, you lose tractability of the model. And it actually becomes often a situation where you have so many parameters that it's impossible to tell which parameters are actually driving the model, and actually any number of combinations of those parameters could end up providing a reasonable fit. But whether those parameters are reasonable or biologically relevant is unclear, because you've just lost track of the number of parameters. And so what we usually try to say is keep it simple. And the idea here is that you have to balance between including the necessary detail of the model and keeping the model tractable. So generally, we advise that you ask yourself, is the mechanism that I'm adding to this model biologically plausible? Does it make sense for me to add active uptake into this tissue? Is it absolutely necessary for me to add active uptake into this tissue? If I do want to add active uptake into this tissue, do I have sufficient support from the literature to both justify the addition of this parameter and also parameterize this new parameter in my model? So again, is it necessary to describe the chemical kinetics, and is there sufficient data to parameterize it? And can I test or validate the parameters? So and just keeping in mind that every time you add additional parameters to your model, you should be sure that you can justify these both biologically and also justify the values that you use in those parameters. Next slide. So, and yes, one of my favorite quotes is, all models are wrong and some are useful. So regardless of the model that you built, there will be somebody that will tell you, oh, I don't know why you used this parameter, or other people saying you should have definitely added more parameters here. There's never an absolutely right model, but what we're looking for is a model that's useful for the purpose. So fit for the purpose for which you have begun building this model. Next slide. So basic modeling philosophy, there are kind of two camps in modeling, and these have been historically referred to as lumping or splitting. So from a lumping perspective, you assume that you begin with all tissues and organs defined separately, and that you only lump tissues together within the model if you have a reason to do so. So you begin with a very complex model that describes in theory all of the processes that could be governing chemical kinetics, and then if you have a good reason, you can combine tissues into a group. If you on a more practical, and personally my philosophy in modeling is the opposite of this is splitting. So you begin with a model that's entirely simple, say a one compartment model that includes all of the body tissues, and if necessary you begin to split tissues out. And so an example of this would be a one compartment model for the body, but then if you recognize that the liver has metabolism that's important to this chemical, then maybe you split the liver out because you understand that you have a reason to describe the liver separately from the other body tissues. A common model structure is a three compartment model where you have the rapidly perfused tissues, the slowly perfused tissues, and the liver separated out. Another example might be separating out the fat, because you understand that this is a lipophilic compound that's likely to be highly concentrated in the adipose tissue. So next slide. The advantage of splitting over lumping is that you keep the model as simple as possible, and it's a much more tractable model. I feel like we skipped a slide. Okay, yeah. So for the tissue grouping, some of the criteria we classically use is the perfusion rate, which is really the blood flow over the volume of the tissue. And the reason we use this is because this perfusion rate really defines, unless you have some sort of active process, then this or a rate limiting process that limits how quickly the chemical can be distributed between the blood and the tissue, then this perfusion rate really defines how much and how quickly the chemical will get into the tissues. So rapidly perfused tissues means that there is a high blood flow to volume ratio, and tissues that fall within this category are the GI, the liver, and the kidney, and others that are rapidly perfused. The slowly perfused tissues are tissues that have a low blood flow to volume ratio, and these include muscle, skin, and fat, and often the brain is included. Well, actually, I'm going to take that back. So, so to look, as you're beginning to build a model, you can look at historical examples of how these models are lumped together, or how these tissues are lumped together for a guide. But the important thing here is that that when your chemical is widely distributed within the body water, then a reasonable way to lump tissues together is based on the rate of perfusion. Another way to determine which tissue should be grouped together is by understanding your model purpose. So if you have a target tissue and you're trying to describe the chemical concentration within that tissue, then it might be useful for you to split that tissue out. If you're interested in blood concentration over time, however, then it might not be necessary to describe as many tissues in detail. And the description of a particular process can also be a determining factor for whether or not you're going to split a tissue out from the rest of the tissues. So as I mentioned before, if you know that metabolism is important to your chemical and you need to describe metabolism, for example, conversion to a reactive intermediate, you may decide that you need to include the tissue in which that metabolism occurs. So you will often see liver separated out as its own tissue, but you may also decide that metabolism within the lung is important, for example, or metabolism within any of the other tissues that Allison mentioned. Intrahepatic recirculation is the movement of the chemical from the small intestine, or from the liver back to the small intestine. And so this can often cause the chemical to stay in the body longer than would be expected without it. And so this might be a case where you decide to explicitly describe the liver and the GI. Protein binding if there's extensive protein binding either in the tissue or in the blood, you might decide to have a compartment for the protein bound chemical versus the free chemical. So these are all types of decisions that you have to make depending upon the chemical that you have. But again, you want to default to keeping it simple and only resort to making the model more complex as is necessary, because every time you make the model more complex, you need to ensure that the parameters that you're adding are well validated and appropriate. So again, it should be fit for purpose. Next slide. So this is some examples of different PBK model compartments. And so we have storage compartments. These are tissues where the chemical can go and remain, can be transported and then remain for some time. An example of these are fat and red blood cells. You have excretion compartments, and these are tissues from which the chemical is excreted from the body. So this might be, the kidney to the urine, the GI to the feces, and the mammary gland to the milk, etc. There are compartments that are governed by flow limited metabolism. So the metabolism is fast and efficient. You have compartments that are also uptake routes, so skin, GI, and blood. Any tissue can be a target tissue depending on where your effect is seen, and any of the tissues can be important for distribution depending on how quickly the chemical is taken up and how quickly it leaves. Next slide. So deciding which tissues to include, I've already kind of covered that, but there are other considerations you might have to make that are sort of more practical. For example, if you're describing an experiment, then you might need to, is complex. And an example of this would be where the experiment itself has parameters that need to be described within your model. So an example of this would be inhalation. Some of the early models were performed with volatile chemicals, and the experiments were performed with rats in closed chambers. And so describing the concentration of the chemical in the air in the chamber was actually an important part of the model. So that's an example. And actually that becomes an issue again when we get into the in vitro modeling in vitro kinetics. And there are other issues that need to be taken into account depending on what type of data you have. And we'll get into that in the course. Next slide. Okay, so this is a very simple compartment description, and I'm not going to spend much time on that here, but we will spend time on that in the course. But I just want to highlight here that what you're doing with these models. So this is one compartment from the model that I've shown a couple of times. It's a tissue. It's just a generic tissue, so that's why that subtext T is there. But you describe the amount of the chemical in the tissue is defined by the blood flow into the tissue, or QT. Q is the blood flow, times the concentration of the chemical in the blood, minus the blood flow out of the tissue, times the concentration in the venous blood from the tissue. And this is the basic fundamental equation for a compartment from a PBPK model. When you put these together, you have the rate of change in the amount of the tissue. If you take the integral of this equation, you get an amount at any point in time. When you divide by volume, you get a concentration in the tissue. And when you divide by the partition coefficient, you have the concentration in the venous blood leaving the tissue. And it's the difference between the chemical coming in and the chemical coming out that defines how much chemical is in that tissue at any point in time. And so it's a fairly simple mathematical construct that then, when put together and solved for the multiple tissues at any point in time, can tell you where your chemical is and describe and even predict where that chemical will be at another point in time. Next slide. So there are two types of parameters that go into models: the physiological parameters. These include body weight, cardiac output, organ weight, tissue volumes, blood flows, the vascular space of each organ. So, and this is particularly important in diffusion limited compartments, where we have to describe the limitation between transfer between the blood and the tissue, and the overall concentration in the tissue is going to be the combination of the amount in the tissue blood plus the amount in the tissue itself. Data for these can be found in references given in the resources section, but these have been pretty well described over the years for most of the tissues in the body. It's pretty hard to find a tissue where you don't have that kind of information at this point. And then we have chemical specific parameters, and these can be more challenging to find depending on the level of information that you have about a particular chemical. So different kinds of parameters include the physiochemical parameters: what's the molecular weight, what's the log P, pKa, information like that. Rates of absorption, so how quickly is the chemical likely to be absorbed through the skin? What's the evaporation rate or vapor pressure? So how likely is it to be absorbed into the lung? Information on distributions, fraction bound for the plasma, and ratio of, say, blood to plasma or red blood cells to plasma, and hepatic clearance rates, other clearance rates. Next slide. And then once you've built the model, you have the challenge of validation. Validation is a pretty broad, sweeping term, and it can be described in a number of different ways, but just as a general concept, validation includes evaluating the fit of the model to the data, but it doesn't stop there. It also evaluates the predictive capability for the validation data. So the important thing here, which we run into again and again in modeling, whether it's PBK or any other type of modeling, is having validation data that was not used for model building, that you use only to test the predictive capability of the model. Validation also includes evaluation of the appropriateness of the model structure, the appropriateness of the model parameters, and you perform this by building an understanding of what's reasonable for this chemical and for this model, for the particular system that you're modeling. And also validation includes evaluation of the parameter sensitivity versus the uncertainty. So the more important a parameter is for your model, the more certain you should be in the value that you use for it. Next slide. I see I'm running over on time, so I'm gonna go through the rest pretty quickly, but this is an example of sensitivity analysis with an ethanol model, and the reference is there. I just want to point out that the larger the bar is, the more important that parameter is for your model fit to the data. And so if that parameter is very important, then it's a parameter that you should have a lot of confidence in. Next slide. Some of the applications of PBK modeling, I've mentioned these, so I think I can skim by them. Life stage, I'd go quickly through these. Yeah, you can account for different disease states and how those disease states affect your chemical kinetics. Next slide. You can use these models to determine how aggregate exposures will come together to cause a particular, or you can predict the chemical concentration in a target tissue based on aggregate exposures or exposures from multiple routes. And this builds on a case study from module 2 with an example chemical phenoxyethanol. Next slide. Okay, and so this is probably what most of you are more interested in, and this is IVIVE, which is actually an extension of PBK modeling, though that's seldom mentioned. So in traditional toxicology, we test the effects of chemicals in animals, and we try to predict what will happen in humans. Our challenge is translating the animal dose response to human exposure, and we use PBK models to predict the human dosimetry from animal data, using the comparative physiology and biochemistry of these two different types of animals. In 21st century toxicology, we test human cells in vitro, and we try to predict what's going to happen in vivo. And our challenge is translating the dose in a cell culture medium to a human exposure. We use modified PBK models, which are called IVIVE models, or in vitro to in vivo extrapolation models, to predict human dosimetry in vivo using physiochemical properties and in vitro kinetics and human physiology. Next slide. So the process is the same. The model, the basic fundamental principles of the modeling are the same. You just use a different model structure and different model parameters. So we do spend a significant amount of time in IVIVE in this course on the background of it and how to perform IVIVE. Just at a high level overview, cell culture dishes are not the static systems that you might imagine them to be and how they're often represented to be. It's actually a very dynamic system. So you're changing the media, the chemical can adhere to plastic, combine to proteins within the media. It can degrade over time. It can evaporate over time. You have the chemical being transported in and out of cells. You might have metabolism in the cells, and you might have binding to the cell membranes or other components of the cells. And so you can have the chemical very dynamic processes happening in the chemical so that your actual concentration of chemical in the media may not be the same as the nominal concentration or the concentration that you believe that you have put into the media. So for best practice, it would be better to measure the media concentration. In reality, this is rarely done. From my experience, it can be a very important activity though. So IVIVE, as I've mentioned a couple of times, an extension of PBK. It's very similar in the cell culture dish. The cell culture medium delivers the chemicals, so this is analogous to the blood in vivo, and the cultured cells respond to the chemical, and this is analogous to the tissues in vivo. However, there are some key determinants of dose in vivo that are missing in the in vitro system, including metabolism that's rarely included in vitro bioactivity assays. Clearance is not the same at all because we don't have the kidney filtering the chemical out of the system at a steady rate, and the plasma proteins may or may not be present, and if they are present, they may or may not be biologically relevant concentration, so they may not be similar to the in vivo system. So you have two approaches to predicting what will happen in vivo based on or predicting an in vivo situation from an in vitro experiment. Either building a system with much higher fidelity, and you're seeing this happen with flow through systems and 3D cell culture systems, but you can also use computational models such as PBK or IVIVE to predict the system mathematically. Next slide. Oh, goodness gracious. So high throughput IVIVE is a very simplified model which allows for the rapid prediction of oral equivalent dose, or that's kind of a term that's going out of vogue now. It's now being referred to as administered equivalent dose to account for the fact that it's not only orally absorbed chemicals that can be predicted with IVIVE, it could also be inhalation or dermal exposure, or any route of exposure of interest. But these models are highly simplified simplified, so they consider only the most pertinent kinetic processes affecting steady state exposure. So that's an important distinction here. For high throughput IVIVE, we're not trying to predict the time course or the changing chemical concentrations over time in the body. We're trying to predict a steady state concentration. And so for this, we need a simplified set of parameters, including absorption, metabolism, urinary clearance, and serum binding. And there are a number of ways that we simplify the process of either assuming 100% absorption, for example, but if that is not sufficient, we also can measure absorption using in vitro systems such as Keiko-2 cells. Next slide. This is the model for high throughput IVIVE. Because it's so simple, it can be summarized in a single equation where you have the dose rate times the body weight over the renal and hepatic clearance. And we also, part of the renal clearance is accounting for the fraction unbound, or the free portion of chemical that's available for renal clearance. And for hepatic clearance, we need to understand the intrinsic clearance, which is associated with metabolism in the liver. So for these very simple models, we only assume hepatic clearance is, the primary source of metabolism. And we also assume that metabolism is a detoxifying event. And so that's an important simplification to keep in mind when you use these models, that they do not account for bioactivation. Next slide. And so in the course, we will get more into these equations and describe how these equations were derived and how we can parameterize them. So this is just a illustration from the seminal paper, Rotroff et al. In 2010 that described the use of high throughput IVIVE to better interpret ToxCast data and the types of in vitro assays we can use to parameterize these models. Next slide. We do need to keep in mind that for these models, we have to scale the in vitro measurements to in vivo values. And in particular, the specific activity for liver clearance is measured as enzyme activity over unit enzyme content. So for example, the nanomoles per minute cleared over the milligrams of protein, that's your specific activity. When you scale that to the in vivo value, you have to consider how the amount of protein in the overall liver. Next, yeah, just keep on clicking. So the specific activity, it would be the same in vitro and in vivo, but the total enzyme content in the system is very different in vitro and in vivo, and we have to keep that in mind, and we have to scale to account for it. Next slide. And this is the scaling values depending on the system that you use: microsomes, expressed enzymes, hepatocytes, etc. Next slide. And this is an example of how IVIVE is important, and this is from another seminal paper, Barbara Wetmore in 2010, describing how they used high throughput IVIVE to put ToxCast bioactivity measurements into perspective and to rank order them. Next slide. Some of the limitations of high throughput IVIVE are that the assumptions that are made to simplify the process and allow rapid assessment don't always hold true for certain chemicals, and in particular, chemicals that are slowly cleared, chemicals that are bound in tissues, and chemicals that are cleared through extrahepatic metabolism. And of course, I've already mentioned this, but it bears repeating: bioactivation. Other processes such as active transport, so active uptake into the liver tissues, active transport into the kidney for clearance, or reuptake into the kidney. These are not considered in the high throughput models. Complex clearance or fat accumulation, other complex routes of exposure. These types of considerations are not included in high throughput IVIVE, but they can be included in IVIVE in general. Next slide. So generally, when we have to use more complex descriptions, we will refer to the IVIVE process as quantitative, or QIVIVE. In Europe, they call it qui-vive. which is quite nice. And this is basically just a more complex description of IVIVE, and it's distinguished from high throughput IVIVE in that you have to add and more closely evaluate some of those assumptions you use in IVIVE. Next slide. There are a number of in vitro systems that can support QIVIVE, and sometimes these will be more complex than our average parent chemical clearance in a suspended hepatocyte culture. For example, organotypic models can be used to collect parameters for, say, liver bioreactors can be used to collect metabolism parameters for slowly metabolized chemicals. You can use modified Keiko2 cells with phenotypic transporters to better understand oral absorption. And there are a number of other more complex and more biologically realistic systems that can be used to better describe kinetic processes as necessary. But again, generally keeping in mind that it's usually advisable to start simple and add complexity as necessary. Next slide. And so this is just sort of summing it all up and how PBPK and IVIVE can be applied to risk assessment. They bring together the chemical dosimetry and in vitro activity to inform risk assessments. And for PBPK, where we begin with animal experiments and we describe tissue concentrations to predict the human external dose at which you might expect to see an effect. And in vitro, we use the in vitro dose response to describe a point of departure, and we use IVIVE to predict the human external dose, which you might expect to see a toxic effect. So while they use different model structures and different model parameters, they perform a similar activity. And I believe that's it. And I'm sorry because I probably ran over. Oh yeah, just to bring us back around to the beginning, this internal dosimetry module focuses on the portion of the next generation risk assessment process that interprets the biological hazard in terms of the dose and allows us to define a point of departure, and that is used in a margin of exposure. I believe that's it. There is a significant amount of further reading in the next slides. And you will have that information to take with you. And I just want to highlight that this is a quick overview, but we will go more into the other, the equations that describe these models in the validation process in the course itself.
Thank you, Allison, and thank you, Rebecca, very much for that tour de force of this module. This module is like, you know, as you can tell, it's very detailed and very comprehensive.